talk about Newton's laws of motion, we're talking about Isaac Newton, a great mathematician and physicist who came up with many of the laws that we will talk about in physics. And Isaac Newton's laws of motion, what he did is he solidified all the thinkings and all the work that a lot of other scientists had done. It does deal with forces. So when we're looking at the laws of motion, we're looking at the forces that are on an object. Other scientists came up with some ideas. A scientist by the name of Aristotle came up with the idea that force is required to keep an object into motion. So that begs us to ask the question, how much force is required to keep an object in motion? And so let's look at it and let's give our answers. A little bit, let's say a little bit, a lot, or none. Those are your answer choices. A little bit, a lot, or none. So let's roll a ball and let's see how much force is required to keep this object in motion. Okay, give it your answer. Let's add another element. What if, does it depend on the mass? So now we have a fourth answer choice, a little bit, a lot, or none, or it depends on the mass. After watching that video, what is your answer? The answer is none. No force is required in order to keep an object in motion. So if we go back to what Aristotle said that a force is required. Isaac Newton came around and solidified the thinking of Galileo. Galileo, if you look up his thought experiments, Galileo said that in the absence of friction, an object will move forever in a straight line. And of course now we know that is to be true. And so Newton's first law of motion, an object at rest tends to stay at rest unless acted upon by an outside force. That an object in motion tends to remain in motion. So an object in motion tends to remain in motion unless acted on by an outside force. So if we look at our tennis ball, why did the tennis ball stop? It's because there was a force of friction on it. If we remove that force of friction, then that simply means that the ball would have stayed in motion continually. That's also why the golf ball kept going when the tennis ball had stopped. So the tennis ball is going to stop sooner because there's more friction on it than the golf ball. This is also known as the law of inertia. And the one thing I'm going to note here, inertia is not a force. Inertia is a property of all matter. So when we say inertia, since objects resist changes in their motion, this resistance is called inertia. And it is directly related to the mass of the object. So if we look at the mass of an object, so an object that has more mass has more inertia, an object with less mass has less inertia. So that simply means this: a bowling ball has more inertia than a ping pong ball. So this one has more, this one has less. So if we look at Newton's first law of motion more, when no net force exists, now remember we're talking about forces, so when no net force exists, an object's motion does not change. That simply means this, that the sum of my horizontal forces plus the sum of my vertical forces equals 0. that means that the object is in equilibrium. So quick question, can an object be moving and have a net force of 0? And of course the answer to that is yes. This is known as the first condition for equilibrium. The units that we use are newtons, and a newton is the amount of force needed to accelerate 1 kilogram of mass 1 meter per second squared. So when we talk about newtons, and we're going to use a capital N when we talk about newtons. So now the problem is identifying the forces that are not on an object. And I want you to reference my video on free body diagrams in order to do that. When we use our free body diagrams or our force body diagrams, that's going to identify the forces that are on an object. And when those forces, the sum total of forces equals 0, then the object is in equilibrium. Another thing I want to point out is that Newton's laws are universal. And that simply means that when Newton came up with his laws, it explained all motion in the entire universe, not just on Earth. See, Aristotle, his thoughts and theories worked on Earth, but they did not work outside of the planet itself. So what's happening on the moon in relationship to Newton's laws are the exact same thing that's happening here on Earth or anywhere in the universe. So all of Newton's laws are universal.